Welcome to Hartman Math. Before we look at functions today, we're going to do a warm-up that's evaluating functions at different values. So go ahead and pause the video here. Go ahead and work through problems 1, 2, and 3. All right, number 1 has two parts, f of 0. If we substitute in a 0 for x, you should have gotten 7. The second part, f of negative 2, substituting in negative 2 for x, 7 minus 3 times negative 2 is 13. Number 2, g of x, substituting in negative 8. Since negative 8 plus 8 is 0, the square root of 0 is 0. Adding 2, you get 2. G of 1 becomes the square root of 9 plus 2. You get 5. And then we see something different where we're evaluating at a variable or a variable expression. So when we substitute or replace x with x minus 8, we get x minus 8 plus 8, which is the square root of x. We cannot simplify that. We do have the plus 2 afterwards. That's as far as we can go there. The reason a little bit tricky. It takes a little bit more. We're going to do f of y. So replacing x with y, we get y squared minus f of 3. 3 squared is 9, so we would initially get y squared minus 9 over y minus 3. And then we can factor that. That's a difference of squares. So y plus 3 times y minus 3 over y minus 3. Now the y minus 3's cancel, so the final answer is y plus 3. All right, today we're looking at lesson 1.4 about functions, the definition of a function. F from a set A to a set B is a relation that assigns each element an x in the set A to exactly one element y in the set B. So set A is domain, set B is the range. So each element in the domain is assigned only one element in the range. For example, at any specific one time of the day, on a particular day, there's only one temperature for that time of the day. So that would be a function in a particular day. Temperature is a function of time of the day. We often see sometimes relations listed as just a set of ordered pairs. So 1 is assigned 9, 2 is assigned 13, 3 is assigned 15, 4 is assigned 15, 5 is assigned 12. So each time we have an input, it's only assigned one output. That also is a function. If there was a second point that said something like 4, 2, that would not be a function. 4 cannot be assigned 15 and then also mapped to 2. So 4 ways to represent a function verbally, as we're just kind of talking through it. That's not very typical. Numerically, by a table or a list of ordered pairs, as we just kind of saw there. Graphically, so anytime we have a set of points or curves or lines on a graph. And then algebraically with an equation in two variables. So testing for functions, in this case we have that set of ordered pairs. And we're trying to determine if y is a function of x. So if we take a look, 2 in the domain has been mapped to negative 2 in the range. 3 has been mapped to 0, 4 has been mapped to 1, so 5 has been mapped to negative 1. It's okay to repeat y coordinates, although we don't have that here. We're really just looking for, do we have any repeat x coordinates? As long as we don't, we should be fine, and it should be a function. So 2 is assigned one output, 3 is assigned one output, 4 is assigned one output, 5 is assigned one output. And that satisfies the definition of a function. That's it. So each element of A is matched with exactly one element of B. It is a function. Checkpoint. So this time we have what's kind of looked at as a mapping. We've got domain, we've got range. Arrows show how it's mapped. So 2 maps to negative 2, 2 maps to 0, 3 maps to 1, 4 maps to 0. If you want to think of that and construct those as ordered pairs, you can. So pause the video here, think about it for a moment. Is this a function? What you're going to see is that 2 has been mapped to or assigned to two different outputs or two elements in the range, which violates the definition of the function. So this is not a function because of that right there, 2 mapping to two different outputs. Not a function. Okay, how can we test algebraically? Well, we'd want to solve for one of the variables. So as it says, let's see if we can solve for the y, see what happens here. Get the y by itself, so we need to get rid of the 4x squared. Let's subtract 4x squared from both sides as we're solving for y. And then if we kind of think, all right, well, is there any x that we could plug in, that we could substitute in that would cause two different values for y? Like if we substitute in a 1, how many different answers do we get for y? We would only get an answer of -2. So that's legal. What about substituting in 0? We'd only get 2. What about 5? -98, but that's the only output. So it seems like each value of x that we substitute in, we're only going to get one output for y, one answer for y. So that's function. All right, part B. Again, we're going to solve for y. So the first thing we have to do is we have to get rid of the -3x. So we're going to add 3x to both sides. We're going to have to undo the squaring, which means square root, but we do have to remember that when we square root both sides of an equation, we're going to get a positive and a negative response. So we would get y equals plus or minus the square root of 3x plus 19. And we're thinking, all right, as we substitute in an x, how many y's are we going to get? Well, for example, if we tried 2, 3 times 2 is 6, plus 19 is 25. We get the square root of 25 is 5, so we've got positive and -5. Positive 5 and -5, that's two different output values, so that's going to mean not a function. Next thing we're going to look at is evaluating a function. This kind of goes back to our warm-up a little bit, really focusing on evaluating functions at variables or variable expressions. So here's our g of x, and we want to evaluate g of x plus 2. So we're going to substitute x plus 2 in for all of the x's. And the only x in our function is right there. So we're going to have negative, meaning opposite of, and that's where we're going to use parentheses. And then we're going to replace the x with x plus 2. Typically, you always want to think of using parentheses when you do the substitution for safety's sake. And then it does get squared. And then we're going to want to simplify as much as we can. So again, keeping the negative out in front, the squaring applies to this. So that means multiplying x plus 2 by itself, x plus 2 times x plus 2, which you can then double distribute to get x squared plus 4x plus 4 when you multiply that all out. And lastly, distribute the negative so we can remove the parentheses to get our final answer of negative x squared plus, minus 4x minus 4. Part B, similar, just the f of x, the function that we're substituting into or replacing into, just a little bit larger. So similarly, we have f of x plus 3. So to evaluate that, we would want to substitute the x plus 3 in for all of the x's in the function. So it's going to go there, and it's going to go there. So replace that x with x plus 3 in parentheses, and that x with x plus 3 in parentheses. So we begin with the substitution step. So negative Parentheses, replace the x with x plus 3. It does get squared, plus 4. Then we replace the x with parentheses x plus 3, and then finish with the plus 1. And then we'll go ahead and simplify, evaluate that one again. Squaring the binomial, x plus 3 times x plus 3. Get x squared plus 3x plus another 3x plus the 9. And this one we just have to distribute. So distribute the negative, and then once you do that, you can combine all your like terms to get our final answer. All right, checkpoint. So go ahead and see if you can evaluate h of x minus 2 using that substitution strategy. Pause the video now, work it through, and we'll come back for an answer. First step is the substitution, so we're going to replace the x and that x with x minus 2 in parentheses and x minus 2 in parentheses. When we square x minus 2, we're going to get x squared minus 4x plus 4. Distributing here, combining like terms, we get x squared. Combine like terms, we get minus 8x and plus 12. Yes, you could factor this, but that was not part of the directions. And factoring just a factor isn't necessarily beneficial unless we're trying to do something with it. So this would be the desired outcome. A little bit different of a function, a piecewise function. F of x is defined as x squared plus x if the input happens to be less than 0. It's defined a different way if the input x is greater than or equal to 0. So when we evaluate, like for part A, f of negative 1, we have to decide which of these parts of the piecewise function we're going to use. Does it fit this condition or does it fit this condition? We're talking about negative 1 is actually less than 0, so we're going to use this part. So we're going to substitute into here, negative 1 squared plus negative 1. And so we would get 1 minus 1, and you get 0. F of 0, well, 0 is not less than 0, so it doesn't satisfy the top criteria. It does satisfy here. 0 is greater than or equal to 0. So this is the one that we're going to choose. We're going to substitute, replace x with 0. So 0 minus 5, and we would get negative 5 there. And for f of 2, that's also greater than or equal to 0, not less than 0. Don't want the top part, want the bottom part. 2 minus 5 gets us negative 3. Next example, example 5, finding values for which our function is equal to 0. And we'll talk about this much later. We're really saying we're finding the zeros of the function. Values of x that make the function equal to 0. So when f of x is equal to 20 minus 3x, as it kind of says, we'll just set that function equal to 0. So 20 minus 3x equals 0. Solve for x. And we've got all of our values of x that satisfy that. So in this case, we would possibly subtract 20 on both sides, and then divide both sides by negative 3. And it's definitely okay to leave it in terms of an improper fraction. All right, checkpoint. Here's f of x. Go ahead and find all real values of x for which the function f of x equals 0. Go ahead and pause the video here, work it out, see if you can come up with any value of x or multiple values of x. All right, so we're going to go ahead and set it equal to 0. One strategy we have is factoring. It does factor fairly nicely there into x plus 8 times x minus 1 is equal to 0. use the zero product property, split those both apart, set them equal to 0. So we get a solution from there. X equals -8, and from here x equals +1, and those are the values of x for which f of x would equal 0. Kind of similar, example number 6, find values for which one function equals another function. We're given two different functions, and kind of like it's suggesting, that is our strategy. We're just going to set the two functions equal to each other. 6x squared is equal to x squared minus 14x plus 3. So now we want to go ahead and solve that. As we do have x squared being a quadratic equation, most likely we're going to want to get it equal to 0. And yes, the easiest and fastest way would be to get rid of this. But one thing you've probably been taught is that in a quadratic equation, it's going to be a lot easier to solve when the x squared or leading term is positive. So if we subtract the 6x squared, we're going to get negative x squared, and that's going to make it a lot harder. So I'm actually going to go the other way and say, let's keep this here, and let's make the right side equal to 0 by getting rid of this and this and this. So if we subtract a 1x squared from both sides, we're going to get 5x squared. Add a 14x to both sides and subtract a 3 on both sides. And now we've got it into standard form for that quadratic equation with a positive leading coefficient, which is going to make it easier for us. So from there, we've got our different strategies for solving quadratic equations. We might try factoring. Not a good one for completing the square or the square root method. If factoring's not going to work, we may want to go back to the quadratic formula. But I do think this one factors. It becomes 5x minus 1 and x plus 3. If we set both of those equal to 0, 5x minus 1 equals 0 becomes a two-step equation that you can solve. And then x plus 3 equals 0 is a one-step equation where this is going to lead to x equals 1/5. And this is going to lead to x equals -3, and those are the two values of x for which the two functions would be equal to each other. Kind of nearing the end, discussion on domain of the function, which you've looked at in a couple previous courses, both Math 2 and Math 3. Talking about values of x which are essentially allowed to substitute into the function. So one of the things that we have to worry about is not being able to divide by 0. So if we look at this one, you're looking at denominators. Any values of x that cause you to divide by 0 cannot be in the domain. And then we also have some limitations on the square root function because we're talking about things that we could graph and put on a coordinate plane. So we're really not interested in creating imaginary values. So although we know we can take the square root of negative numbers in the complex system, we're really kind of limiting ourselves to the real number system here. So non-negative numbers only. So we have to kind of exclude the negatives as well. All right, so find the domain of the function. Example 7, part A. If we're just given a set of ordered pairs, should be pretty easy to get our domain. The domain are all the inputs, the -3, the -1, and the 0. There are 3 values, so we're going to list it in the braces because it's a finite number of values. And it doesn't technically matter which order that you write it in, but typically you're going to see me go from smallest to biggest, no matter what the order is up here. G of x equals, okay, so we have two different issues down here. One, that the denominator is not allowed to be 0, and that it's not allowed to be negative. It's not allowed to be negative inside of the radical because then we would get imaginary values. So we're really, there's a couple things that are going on here. It has to be greater than or equal to 0. Because of the imaginary situation, but because it's part of the denominator, it also cannot be 0. So if we just think of it, x plus 5 is going to have to be greater than 0. So if we start there, anything that's greater than 0 for x plus 5 should work for our function, and then solve for the x. So we're going to get, if we subtract 5 on both sides, x is greater than negative 5, and typically we're going to want to really default to using interval notation. It does not say or equal to, so we're not going to use a bracket. So we're going to start at negative 5, comma, and we're going to go all the way to, since we're not going to stop, any value larger than, essentially we go to infinity there. Always use a parenthesis in terms of infinity when we're talking about interval notation. All right, example number 11. This kind of goes back to one of the things we were looking at before, evaluating functions at variables and variable expressions. This is the difference quotient. This symbol, when you see it, is going to refer to, this is going to be something you're going to see in calculus. Okay? So here's our function. It probably should say f of x is equal to. And it says find this value. So we're going to have a fraction, and we're going to substitute, most of the work is going to be right here, substituting x plus h into this for all of the x's. So that's going to kind of take us back to the previous example where we've been working on that. So here's our difference quotient. It's just exactly what you see here. Now we get into the substitution. So we're going to see how I've replaced the x with x plus h, and that x with x plus h. And since there's a lot of parentheses, I chose to use brackets to kind of group this expression right here, minus f of x, which is right here. That has to be in parentheses as well. The whole thing is divided by h. So we're going to just now simplify and see what happens. As you go through this process, you're going to see that there should be a lot of cancellation as we go through. So if we think of this as x plus h times x plus h, go ahead and kind of side work that out. X times x is x squared. X times h is xh. There's another one of those, so 2xh plus h times h is h squared. Distribute here. We should get to there. So this becomes that trinomial. This distribution becomes there. Plus 9. Distribute the minus. And then we're going to see there should be a lot of cancellation. X squared cancels with negative x squared. Negative 2x cancels with positive 2x. Positive 9 cancels with negative 9. So now what we have left, we're going to divide by h. That does distribute. So if we divide each particular term by h, we would get 2x plus h minus 2. And since we are dividing by h, we do want to stipulate that that cannot be 0 since we're never allowed to divide by 0. So kind of get in the habit, when you're doing the difference quotient, of also giving the condition, my h is not allowed to be 0. And that's it for today. We'll see you next time.